Think about it. From your bank account to your web browsing to the entire world of blockchain, our digital lives are built on a foundation of trust. And that trust, it all hinges on one incredibly powerful idea: cryptography. So, let's pull back the curtain and explore the hidden world of secret codes that keeps everything running.
This is the question, right? It's the oldest problem in the book, something spies and generals have wrestled with for centuries. In the world of cryptography, we give these folks names. We call the sender Alice, the receiver Bob, and the person trying to listen in, well, we call her Eve, the eavesdropper.
So how do you do it? How does Alice get a message to Bob without Eve being able to read it? Let's start with the basics.
At its core, that's what cryptography is all about. It's the art of secure communication when someone might be trying to intercept it. It's basically the science of turning something that makes perfect sense into what looks like complete and utter nonsense to anyone who doesn't have the secret.
And this is the fundamental trick. We start with plain text. That's just our normal readable message. Then, using a secret key, we scramble it up into something called ciphertext, which is just an unintelligible jumble of characters. The whole point is that only Bob, who has the right key, can unscramble it and turn it back into plain text.
For like thousands of years, the way this worked was pretty straightforward. It's called symmetric encryption. Alice and Bob share one single secret key. Alice uses it to lock the message. Bob uses that exact same key to unlock it. Simple, right? But here's the million-dollar question. How did they get that secret key to each other in the first place without Eve, the eavesdropper, getting her hands on it? This is the key exchange problem, and believe me, it is a massive weakness.
But then, in the 1970s, a totally revolutionary idea came along that just flipped this whole problem on its head. And it's what laid the groundwork for the secure internet we all use today. So instead of one shared key, what if you had two keys? A pair of keys that are different but mathematically linked together. This is what we call public key cryptography. One key is public. You can shout it from the rooftops, give it to anyone you want. The other key is private. You guard that one with your life. And here's the genius part. What one key locks, only the other key in the pair can unlock.
The best way to picture this is the mailbox analogy. Imagine Bob hands out copies of his open padlock to the whole world. That padlock is his public key. Now Alice wants to send him a secret message. She writes it down, puts it in a box, and snaps Bob's padlock onto it. She can now send that box out in the open. And here's the magic. Anybody can lock a box with Bob's public padlock, but only Bob has the one-of-a-kind private key that can actually open it. He never had to share his secret. Problem solved.
Now, this wasn't just some clever theory. It quickly became the absolute backbone of our digital lives, working behind the scenes in all sorts of ways you probably don't even think about.
You know that little padlock icon you see in your web browser next to the URL? Well, every time you see that, you're looking at public key cryptography in action. Technologies like SSL and its newer version, TLS, use the website's public key to create a secure, encrypted tunnel between you and the site. It's what protects everything from your banking login to your credit card number when you're shopping online.
And guess what? It's the very same technology that makes the entire world of cryptocurrency possible. Your public key acts kind of like your account number. It's the address people use to send you crypto, but it's your private key that proves you actually own those assets. It's like your digital signature, allowing you to authorize transactions and nobody else can fake it.
I mean, this quote from Coinbase really says it all. In the crypto world, your private key isn't just some password. It is your ownership. If you lose that key, you lose your assets, period. It is the absolute ultimate proof of control.
So, for decades, this system has been incredibly secure. The math problems it's built on are just way too hard for any normal computer to solve. But there's a new kind of computer on the horizon, and it changes absolutely everything.
See, here's the thing. Our current security isn't based on these math problems being literally impossible to solve. It's just that it would take a regular computer thousands, maybe millions of years to do it. So what happens when a new kind of computer comes along that can solve them maybe in a few minutes?
This is what we call the quantum threat. A powerful enough quantum computer wouldn't have to guess your private key. It could actually calculate it just by looking at your public key. The whole mailbox analogy would be shattered. And the fallout? It would be catastrophic. Every secure email, every private message, every single financial transaction ever sent could, in theory, be cracked wide open for anyone to read. That's the risk we're talking about.
And you know, this isn't some distant sci-fi fantasy. The tech giant Google has actually put a date on it. They've set a public deadline to make their systems quantum resistant.
2029. The race is on, and the clock is officially ticking.
Okay, so the good news is that the world's cryptographers are not just sitting around waiting for this to happen. The race to build the next generation of security is already well underway.
Welcome to the world of post-quantum cryptography, or PQC. The whole goal here is to find entirely new types of hard math problems that are so complex that even a powerful quantum computer can't solve them. It's like we know a master lockpicker is coming. So we're not just trying to build a slightly better lock, we're inventing a whole new kind of lock that their tools just won't work on.
And this is happening right now. In the US, the National Institute of Standards and Technology, or NIST, is in the final stages of standardizing these new quantum-resistant algorithms. And huge companies like Google are already building them into products you use every day, like Chrome and Android. The plan is very clear. Upgrade the world's security before the threat becomes a reality.
So it's this incredible, high-stakes race between the code makers and the code breakers, and it's happening as we speak. The security of our entire digital future really depends on who wins. The question isn't if our current digital locks will become obsolete, but whether we can invent and deploy better ones in time.